In the first semester of business mathematics or introductory mathematics courses, we discussed the concept of limit and derivative in detail, starting with functions. In these chapters, we studied the derivative and its application especially. In this chapter, we introduced to integral the second key concept of calculus. First one was the derivative. The integral can be used to calculate areas, volumes, the index of income concentration, and consumer surplus. You may consider there is no relation between the integral and the derivative. However, there is a close connection between these two concepts, namely derivative and integral. This connection or relation will be given in the fundamental theorem of the calculus. In the section 5 of chapter 5, you will see. We consider many applications of integral and differential equations in this chapter. Let's start the chapter 5 from the section antiderivatives and indefinite integral. As you know, many operations in mathematics have reverses. For example, addition is the reverse of the subtraction, multiplication is the reverse of the division, powers and is the reverse of the roots. We now know we now know how to find the derivative of many functions. So, what is the reverse operation of the derivative? Actually, the reverse operation, which is called anti-differentiation or antiderivative, will receive our attention in this and the next 2 or 3 sections. So let's start from the antiderivative. Antiderivative. A function, capital function f, is an antiderivative of a function small f of a function small f if and only if f prime equals f of x, the capital F prime, derivative of capital F equals f of x, small f of x. As you know, the capital F is not unique. So because of this reason, this is the one of the antiderivative, okay? An antiderivative, not the an antiderivative. For example, derivative of the x cube over 3 is x square. So x cube over 3 is an antiderivative of the function x square. This is small f of x. Why? Because derivative of the capital F of x is derivative of the x cube over 3. In other words, this is 3 times x square over 3. So which is f of x square. So this is f of x. So this implies derivative of the capital F equals small f of x. So f of x is the antiderivative of the x square. But it is not the only antiderivative of x square. Okay. For example, derivative of the x square over 3, sorry, x cube over 3, I'm sorry, plus 3, or maybe 3 is very special number, so let's say 1, is also x square. Or derivative of the x cube over 3 plus any constant number, okay? Let's say minus e, for example. Minus e is again x square. So this implies x cube over 3 plus 1, comma, x cube over 3 minus e are antiderivatives. Antiderivatives of f of x equals x square function. In general, x cube over 3 plus c is for the family of the all antiderivative, okay, is let's say n antiderivatives of x square. But this is the family of the all antiderivatives, okay? So let's note by the capital F of x. So this is the family of the all antiderivative. You can say that if f and g are the antiderivative of the small f of x, in other words, capital F prime and capital G prime are the same. So there is differences between the f and g constant terms. I mean, with the constant term, I mean f and g are antiderivatives. Derivatives of the small f of x equals x, not x square, any small f of x, okay? So f prime is small f of x and g prime is small f of x. So this implies f prime equals g prime. Maybe you can say f prime of x, g prime of x, there is no problem. Okay, so let's say capital F prime of x, capital G prime of x. So capital F prime of x equals g prime of x. So this implies f of x equals g of x plus k. Okay, so as a theorem, we can give this result. So if you know one of the antiderivative of any small f function, you can write the all antiderivative by adding the constant key terms. Okay, here where key is constant, any real number. Now, by using the concept of antiderivative or the family of the antiderivatives, we can define a new notation which is called the indefinite integral. So, I mean, the integral of the capital F prime of x dx equals capital F of x plus c. Actually, why we use this notation? So to obtain the reverse operation for f prime, I mean capital F prime is derivative of the capital F. So by integrating, you turn back the f prime. I mean, okay, let's try to explain this by using this diagram. You have a function f of x. So by differentiating, you obtain new function f prime of x. This is the derivative operation. So as an inverse operation, we use the indefinite integral. Indefinite integral. But of course, we lost our constant term. I mean, if capital F of x is, for example, x cubed over 3 plus 1, so f prime of x is x squared. So when turning back the inverse, by using the inverse operation integration, the integral of the f prime, it can be any function, f of x plus c, okay? So this is derivative, this is integration. So here, f of x can be any number, x squared, x cubed over 3 plus c. Why? Because derivative of the x cubed over 3 minus e is also this function. So we cannot know which function is our original function, okay? So this operation, inversive operation, is called a indefinite integral because it is not definite. We have a constant term c. Since we know some derivative formula, we can obtain some basic integral formula for the indefinite integral easily. For example, we know derivative of the xn plus 1 over n plus 1, derivative of this function, is n plus 1 times x to power n plus 1 minus 1 n over n plus 1. And these terms cancelled, then we have x to power n. So xn plus 1 over n plus 1 is antiderivative of the xn. In other words, we can conclude that is capital F of x. This is derivative of the f of x. So integral of the f prime of x dx equals capital F of x plus c. So that's imply integral x to power n dx equals x to power n plus 1 over n plus 1 plus c, okay? So we obtain this important indefinite integral formula. And similarly, we can obtain some other formulas. Integral of the e to power, derivative of e to power x is itself. So integral of the e to power x is e to power x plus c. Any constant term can be a. And from the derivative formula, integral of the 1 over x dx is ln absolute value of the x plus c, because derivative of the ln x, since derivative of the ln x is 1 over x, and here since derivative of the e to power x is e to power x. So by this way, we can define the indefinite integral. By using antiderivative, actually, we can describe. And we have some properties for the indefinite integral. So let's give quickly these properties. The first property is derivative of the key times small f of x or capital F of x, does not matter, okay? You can use this in notation, equals key times integral of the f of x dx. If I set the derivative, I'm sorry, integral of the key times f of x dx equals key times f of x dx. What does it mean? You can write the constant term outside of the integral, outside of the indefinite integral. And the summation of two, or differences of the two function, integral of the two function, let's write the differences also, equals integral of the first function plus, or if it is subtraction or minus, integral of the second function. Okay, both of them comes from the formula of the derivative. Actually, you can recall what we know, that derivative of the okay, let's write, since derivative of the key times f of x, maybe this f not the same, so let's use another notation, g of x with respect to x equals key times derivative of the g of x. So because of this reason, for the some different notation, of course you can explain, this is we obtain that formula. And for the second one, because of the summation of the derivative, so derivative of the, let's use some other notation, h of x plus or minus k of x equals derivative of the h of x plus or minus derivative of the k of x. Because of this reason, we obtained that properties. Okay, you can find the proof or explanation of the these properties in your textbook easily. Also, you can find some application in your textbook. I will solve these questions in the lecture